Okay, good morning everybody. I hope everyone's having a wonderful day. So before we get started, I just want to point out that assignment 1 has been released. It is due by the end of May 18th. As noted, the submission will remain open until 8:30 of the following morning. So on the 19th, the submission will remain open until 8:30 in the morning Regina time. So what does that mean for you is that just like I mentioned during the first lectures, I normally like to leave a little bit of a gap there so that just in case there's any technical issues, or say for example, it's like 12:05 and you're like, hey, look, I want to hand in my assignment, but oh, some weird thing like the website took longer to load or something, or your internet went out for like a couple hours. That way you can still submit your work and you don't have any issues when it comes to at least technical matters. But when it comes to that, you're welcome to use this time as you see fit. Don't use the dog ate the assignment excuse. It won't go very well unless I don't know. I haven't encountered that one yet. Usually the more common one is that, oh, my hard drive got corrupted, which is terrible. Like, that is legit terrible. But that's why in the course outline it talks about backing up your work. But yeah, no. So just to be very clear, the submission for this assignment would close at 8:30 in the morning on May 19th. There's no late assignments accepted after that point. So even though I say the end of May 18th, that's the on-paper deadline. So that extra bit of time there, that's just me giving you some leniency just in case there's any technical matters, but you're welcome to use that time as you see fit. Just know that after 8:30 in the morning, I won't accept your assignment. So hopefully that's clear. I'll be releasing a discussion video. It'll be posted on the course website itself. It'll be an unlisted video. It'll talk about the assignment 1. So if you want to, if you're looking at the first assignment, you're like, okay, I want some tips to kind of approach these things, I'll be making a video that will be going through that. But keep in mind, you don't have to watch this video at all to be successful on the first assignment. These are just tips to kind of walk through things, because in this course, we have a lot of fun stuff we got to talk about, and I just got to make sure I keep the ball rolling, okay? So hopefully that's clear, everybody. So like I said, I just want to remind you, I recommend you start working on the assignments as early as you can. So you'll see that there's certain things that we can cover up to some point in this assignment. So I recommend you start thinking about the first problem on the assignment by next week. That's one thing I would recommend you try doing, is just start thinking about the first problem. It'll have a lot of the machinery for working kind of on the first half of the problem. So anyways, actually, are there any questions before we proceed? Any questions at all? Are we all good to go? Excellent. Give me 2 thumbs up if we're all ready to go. Today we're going to talk about algorithms. Awesome. Awesome. Okay, so why don't we get on this? Let's start talking about algorithms. So last day I drew you a fun picture on the board that connected the idea of a problem, which consists of problem instances, and we had this idea of an algorithm, which I'm sure that we have an insight or intuition around what an algorithm is, but I want to give us a nice working definition for us at this level. Now, further on in your studies, you'll probably learn a much more rigorous or rigid definition of what an algorithm is. But at this point, this working definition will work well enough, especially if you're interested in things like algorithms. This will work perfectly fine if we're interested in problem solving. So here's a definition I'm going to give you, and I'm going to break it down and try to explain it in much simpler terms. So here's how I'm going to define an algorithm for you in this class. It's not a perfect definition, but most certainly it's good enough for a working definition. Even researchers could use this definition. It's perfectly fine. But it relies a little bit on your intuition. So here's what I'm going to give you. It's an unambiguous step-by-step procedure that takes an instance. So when I talk about an instance, I'm talking about a problem instance as inputs and produces output for the problem instance. So the algorithm does this step-by-step procedure. It's given the input, it produces output. So normally this is done in the context in the most broadest sense. Usually you'll find in our course, a lot of them will be where they actually return something, just like a function might return. that's very common, or we might compute something that modifies some data structure. So here's the idea. So I take an input, produces output, and the big thing for us, which I will come back to this a couple words in here, is that we talked about this at the very end of class last time, is that when I get this output, I would like to know that it's correct, right? And so what's a definition that works for us for it being correct? Well, the output's correct if it is the solution to the instance, right? This is something that we discussed together last time. So there's a couple of things I really want to kind of parse with this. So the first one is this notion of unambiguous. Now, for some of you, you may or may not have seen this term before. It's related to a concept called ambiguity. So when I give you a process, I would like to have it so that if I can give and describe it to you, that there is no way it can be misinterpreted to your audience. So I usually like to tell a little story just to kind of illustrate this idea. So sometimes on my trips, I see this sign off the side of the highway. And on this side, it's a business sign. I don't obviously want to go into the details of this business, but it reminded me, it's very similar to this. On this side, it would say combat animal control. And it would have like a phone number here, call us, etc., etc. It's just a sign off the side of the highway. So I would see this sign, and me being me, I'm just sort of like, hey, look, I'm a big stickler when it comes to having things very exact, where they aren't ways I can misinterpret something. When I read this sign, I found this very fascinating. So, for example, when I read this, it says combat animal control. Now, there's at least a couple different ways I could interpret this sign, right? There's at least two. There could be many others, obviously. Now, the first one is I can look at this and say, okay, well, combat animal control, that's like the name of the business, right? That's how a usual person that has some intuition of how billboards work. It's like, okay, this is saying, oh, combat animal control. But say I don't really have that intuition at all. Say I'm really like looking for a message very carefully. Well, another way I could interpret this sign is it's saying combat animal control. So notice it's saying combat animal control as I have to combat animal control. Like, is this supposed to be a sign that's telling me about a business, or is it telling me a message to combat animal control? Do you see what I mean? Like, it could be potentially ambiguous if I take it literally. Do you see what I mean? It's a little bit unclear if you take it literally. And the thing is, when we describe algorithms, we need to make sure that they are literally in a way that I can't misinterpret it. So what I mean by unambiguous is there's no way I can interpret it in a way that is not what is intended. So that's a big part of it. And the big thing when I say this is that when you present an algorithm to somebody, it could do it in words, you can do it in, like as a computer program, you can do it in what we're going to see as pseudocode. That's going to be something we're going to see a lot of in this course. Normally what I do is I communicate it to you based on your understanding of where things are. So for example, I might talk to, say, a room of experts on, say, combinatorial optimization. It's an area I'm interested in, about a given algorithm. In a different way, I might talk to you in this lecture hall about it, right? I might do that, but that's because my audience knows more about the subject. It's because they've been doing it for years and years and years. So that being said, it's very much how you tailor it to your audience. So here's the great thing though. Computers, especially when you think about tangible computers, such as the one you're probably watching this on, the great thing about that is that when I give you a computer program, the way you describe it to me is sequentially, right? By key instructions. And those, in fact, are naturally saying. They're very natural to describe somebody, but they're also exact. So you're going to find that when we talk about algorithms, having an exact description of that algorithm is very helpful for us. But you're going to see that I don't necessarily want to tether it to only one way of saying something. Sometimes I would like to have a kind of a general recipe regardless of which programming language I use. But at the same time, I would like to be able to make sure it's clear to the reader. The big thing is clarity to the reader. So is this idea of unambiguous make sense to everybody? So ambiguity is when you have two possible ways you can interpret the same thing. We don't want that to happen. So usually you got to think about it more from the matter of how you communicate it. And for a computer, well, I can't just like tell the computer to make some pancakes for me, right? I have to actually give like explicit instructions in a very unambiguous way to the computer to do this. And that's why the notion of an algorithm is very useful for us. If we think about it from a practical standpoint, if we're thinking about physical computers, but also if we want to solve problems, I can communicate the idea to people and they can carry out that process. I don't have to worry about somebody twisting it and doing something that was unintended. And this other word that is doing a lot of heavy lifting in this definition is step-by-step procedure, which I have not formally defined. That is something that I'm lending myself to your intuition because you've seen computer programs before. Computer programs are these step-by-step procedures, right? We have one instruction that comes after the other, right? Then you have different control structures such as loops, you have like if statements. Like this is stuff that we're familiar with. So this phrase here is doing a lot of heavy lifting. In future courses, say a course like CS210, you'll see a much more exact definition than this. But that being said, are there any questions about this definition? Is this good enough for everybody? So this connects a lot of the pieces that we've been talking about up to this point. So I thought it would give us a few examples of algorithms that I know you've seen before. So for example, for sorting, so some algorithms. Can somebody tell me an algorithm that you can use to solve the sorting problem? I know you've seen more than one. Yeah, so I got one so far. I got insertion sort. That's a good first one to talk about. Insertion sort. Selection sort, very good. I heard selection sort. There's some more out there too. There's one that usually people like to grill a lot as well. Binary sort. Now there's binary search, which we'll talk about again later on in the course, but there's bubble sort is the other one I was looking for. There's other ones like merge sort, and there's some other ones. We're going to talk actually about merge sort later on in the course too. There's a lot of different sorting algorithms out there, which are very fascinating. But yeah, I'll throw bubble sort up here just because it's among the kind of family of these classic comparison-based sorting algorithms that you may have seen or gotten familiar with in something like 115. We'll see some more sorting algorithms in this course. Some of you may have heard of before. I had seen merge sort, for example, mentioned. We will talk about merge sort in this course. We'll go into the nitty-gritties with it. But you see that you've seen a lot of these things. I'm just putting all the pieces together so that we can kind of talk about it in a much more careful way. So notice that each one of these algorithms solves the sorting problem. I can give you any arbitrary array of length n. So for example, I could give you any possible array of length 5, 10, 10,000. Any one of these is capable to be solved by any one of these three algorithms, right? Now, notice that I haven't said anything about their efficiency. Just that I know that they're capable of solving solving the sorting problem. That's what I know. So that brings me to one important point, is this notion of correctness. So I planted the seed last day about this, but it's important that computer scientists tend to strive for algorithms that actually produce correct output always. That seems to be the gold standard. Because ultimately we want to solve problems, right? It isn't just that I want it to work like I don't know, every one in like 500. Sometimes it just has this weird blip where it just doesn't work properly. That isn't really what we want to go for in this course. We want to actually have it where we give an algorithm, it always will work, and always working in the sense that we're talking about, it means that it solves the problem. But what does that mean? That means regardless of which input I give you from some instance, so any instance of the problem, my algorithm has to produce correct output. So that is the standard that we're working by in this course. And that's a very fundamental computer science one. Because we normally, one of the backbones of studying algorithms is to know that things work the way you expect them to, right? You don't want to give somebody an algorithm that you implement on a computer and say, oh, well, every once in a while it just sort of does this weird blip and then it just doesn't work anymore. That is not an ideal feature of an algorithm, right? And nonetheless, that is ignoring the fact that we're trying to solve a problem. So I'm just going to remind you that an algorithm is correct. So this is what I'm going to refer to as a correct algorithm. So an algorithm is correct if for every instance of the problem, the algorithm always produces correct output. So that's very important, right? So you don't want to have it where you're trying to claim you solved the problem, but I can find you at least one instance where it fails to achieve this. Does that mean I've solved the problem if that happened? So if I give you if I presented you an instance of a problem and the algorithm doesn't produce correct output, does it actually solve the problem? Yes or no? No, right? Yeah. No, very good. Very good. Yeah, it doesn't. No. So that's actually very often a way if you wanted to tell somebody, hey, look, I claim this algorithm works. How can I know it doesn't work? Well, one way you can evaluate and do this is by just presenting one instance of the problem, show them it doesn't work, as in it doesn't produce correct output. That's actually all you really need to do to show an algorithm is incorrect. It's really that simple. Now you might say, Dan, well, how do I know which instance to pick? This is normally when it's important to be able to study the algorithm itself. So learning a bit more about the algorithm, you can often tailor an instance to do this. So it's definitely not something that's very easy to do all the time. Sometimes these algorithms can be very sophisticated, especially in practice. So I want to mention that there's kind of two standard criteria that we can use to prove correctness of an algorithm. To prove an algorithm is correct, we show two things. Oftentimes, these are two things that are separately shown, and then you bring them together, or sometimes it's explicitly done at the exact same time. In this course, I think it's easier to see them done separately because when you prove one of these two things, it makes it easier to prove the second one. So if you prove the first one, it makes it easier to prove the second one. But we'll see an example today what I mean by this. The first thing is that the algorithm actually terminates, right? So notice that in my definition, it has to produce output, right? That's an implicit thing. Did anybody catch that? It's very implicit in my definition that it produces output. So when I say produce output, I'm just saying it returns something, but I'm just keeping it as broad as possible. But that means that the algorithm has to terminate at some point, right? So the algorithm terminates in finite time. The algorithm terminates in finite time. So this is a termination condition. So I just want to make sure that it terminates in finite time. So this is regardless of which instance I give you of the problem, it has to terminate in finite time. So knowing this fact, I can then look at whether the output is actually correct or not, because I know it always will complete, right? It's not going to just suddenly go somewhere and get stuck in an infinite loop, right? So that brings me naturally to the second one, is that the algorithm produces correct output. But you can see how, so this is just the second part, is just correct output. So one thing I want to point out again, like I said, is that a lot of the time when you run into what we refer to as proofs of correctness, oftentimes this first part is implicit in the second part. But very often you have to make sure it actually does terminate, right? So if you ever run across a lot of these proofs of what we call proofs of correctness, or a proof of correctness, hence why we call it proof of correctness, because we're trying to show the algorithm is correct. That's where the phrase comes from. So a proof of correctness. So this constitutes a proof of correctness. So proof of correctness, this is how we ensure that the algorithm actually works. Now, last day I talked about how, oh, you have a computer program, like you could implement the algorithm on a computer, right? Like I could write up my algorithm, like I could take like selection sort, I could implement that in C++ on a computer, right? Now, like I said last day, well, how would you actually show me that it actually always works for every problem instance if I define the problem to have an infinite possible number of problem instances? Well, it's not straightforward, right? You can't just simply just sit there and just grind out every single problem instance just like it's a test suite or something. You actually have to sit down and actually think about what the algorithm is doing. And this is the great perk about this, is that the algorithm is unambiguous, so it has an exact definition. That means that we can study it using our favorite tool, the mayonnaise, that dreaded mayonnaise. It makes good sandwiches. That's all I'm going to say. So every once in a while, it's going to be important for us to pull out that tool out of our pocket and put it back behind our ear, because it's a very valuable tool for us if we want to ensure that an algorithm is correct. So are there any questions before we proceed? I thought it would be a good idea we do an example where we revisit the one we talked about called the search problem earlier. I thought it'd be a good idea we kind of just see how all of these pieces work when we actually have a problem. But are there any questions before we proceed? So all I'm doing is I'm just formalizing a few things that you may be saying, oh, Dan, that's pretty basic. But at the same time, it's important that we have some way of talking about these things in a way that it isn't unclear for somebody. Okay. So if we're okay, let's boogie on over here. So I thought it would be a good idea we start off with the search problem in the way that I said last day. So recall, for the search problem, I have an array, or we thought about it as a set S with n elements in it, and I had a key, right? And my goal was to determine if the key is in the set or not, where I had that key X. For us in this discussion, we'll just assume that the set S is just an array L that stores n integers. So here's an example of what one of the problem instances would look like. Here's an array. It has 10 elements in it. And I have a question for you. What would be the input size for the search problem? Or at least what's one reasonable consideration for the input size? I think the latter is far more relevant for us. So what would be the input size for this problem? So notice that in this problem, there's actually two inputs. I have this array, and I'm also going to have some key. So I'm going to have a key here, key X, and it's going to be some value. And I want to know if it's in the array L or not. So for example, I can put, well, let's go. If I gave you X as 22, what would be the input size here? I'll tell you a straight up answer is that it's very similar to one of the examples we seen last day when we talked about input size. So just think about it. I have an array. It has n elements in it. And I have just this extra integer that's just kind of sitting off to the side. Now, it'd be easy enough to just measure the input size based on just what the array is, because that's just one number over there, right? That's just an integer. But there's just one of them, but I have n of them over here. So one reasonable consideration for the input size would just be the size of the array. Yeah, so n would work perfectly fine for us. And like I said, you can always whittle down this way further. Like if you want to literally be like, hey, look, the number of bits used for this number, this number, this number, this number, this number, all of these all are some log base 2 of some number of bits or bytes. Then I have this n times, then I have another integer over there. You can measure these things in very exact terms if you really wanted to. But a reasonable consideration for this problem would just be the size of the array. So just the size of the array would be good enough for us. You'll notice that for this problem, the thing that grows in terms of the size of the input is the length of the array. I always just have one number over there, right? So that's one intuitive way you could see why I would just not even consider what x is. But like I said, there's several different ways you can consider the input size. The more natural one is to look at the thing that actually can grow with the input, in this case, the array. Because we care about the number of elements in our input. In this case, I just have one extra. If you said like n plus 1, that's okay. But most certainly, n is good enough for us because we want to measure the running time with respect to the input size. And n is a much easier number to work with than n plus 1. So anyways, if I give you this search problem and I give you this key, say for example 22. Where is 22 in L? I can tell you up front it is in that array, right? So somebody's asking about why n plus 1? Well, you have n elements in this array plus that one number over there for x. So some might be like, okay, well, there's n plus 1 numbers there, right? That's how somebody might come to a conclusion of n plus 1. But most certainly, it's easy enough to just pick n. Yeah, no worries. But what position is 22 in this array? So if I gave you this as a problem instance where I have this array L and I give you x is 22, what should be the solution here? Well, first it's there, right? But I want to know what position it is. Yes. Yeah, it's in the 6th position, position 5. So in this case, if I give you this instance, it better, so if I want to know what position it's in, which I can implicitly use to tell me if it is in the array or not, if I just return this position, so I just return 5 in this case, that tells me it's there, right? Yeah, it's in L sub 5. Very good. So I can just tell you the position, right? That tells me right away that it's there. Now, how about if I change this to something else? Say, for example, let's make x, this key, be 8. So if first, like, natural question, is 8 in this array at all? No, right? So you know in this case that it doesn't have a position in here. One standard way to deal with this is that we would just simply say, okay, well, it's not in the array. If I give you a position, I can just tell you that it just returns -1. -1 isn't a valid position in this array, by the way. So it's okay for me to have that. Now, if I want to formulate in the exact way that I gave you the search problem last day, I would tell you whenever I give you a number that isn't -1, then you would say true, yes, it's in there. Or if you give me -1, it's false. For the sake of our conversation here, I'm just going to consider when we need to find the position. But you can see how easily you could just modify what I've just described here with using an if statement, right? You could just check if you have this as a variable, like if pos is equal to 5, or isn't equal to -1, then you know you can return true, otherwise you return false, right? You can easily modify what we're going to do here to do that if you need to. I think it's just easier to play around with the positioning here. So here's the cool part. I think you know a way to solve this problem. Does anybody have any suggestions? So I thought I'd bring out some lovely friends here. This is my crew. I thought I would bring out some of these. So say, for example, these are my numbers here. I brought everybody. I bought a lion, I got a horse, I got a zebra. I even got a dinosaur here. I've got a lovely cowboy. The question is, okay, so how could I ensure if I have that key, how do I ensure I could find it in here? Can somebody just tell me a good idea to maybe approach this? I must stress that you probably have seen this algorithm before. So remember, my goal here is I give you the array, I give you X. I want to know if it's in the array, tell me where it is, to which position. Otherwise, tell me -1. So there's a very classic way of doing this. Now, I must stress, and this is one that I always like to hear about, is somebody brought up binary search. Now, here's the neat thing. The instance I gave you explicitly right here, notice that it actually is sorted from smallest to largest, so you could technically use binary search on this input. But remember, the search problem doesn't actually say anything about the array being sorted, right? We don't know that the collection of elements is sorted. So could I use binary search generally? So if I give you any array L and any X? The answer would be, of course, no, because binary search requires that the input in here is sorted. But I see another one mentioned. It's called linear search. Some people call it sequential search. I'll call it linear search. So the idea is really simple. So I would just start at my first position. And say, for example, I'm looking for that fun dinosaur. I'm looking for the dinosaur. So I could start here on my leftmost side. I could check, is the lion a dinosaur? Nah, right? So I could just check the next one. Okay, the horse, not a dinosaur. Okay, I'm going to go here. Zebra, that's not a dinosaur. I found the dinosaur. So I would tell you where the dinosaur is. So notice this, if this is position 0, that's position 1, position 2, and position 3, I would return 3. But if I was looking, for example, for a lovely green giant or something, notice I don't have a green giant in here, right? So notice that in that case, I would return -1. So this is the exact idea that I would like to use. I would like to go sequentially, position to position. I'm going to sweep from left to right. And if I find a match, I want to return that. So this is the idea of linear search, right? So we got to talk about that. So we know an algorithm that solves this problem. So we can use linear search to solve this problem, right? And the intuition behind linear search is really great because what it does is it starts at the leftmost position and it sweeps to the right until we get a match, right? But if I sweep over all the elements and I examine every single one of them, I haven't missed a single element, right, in the array. So this is a very important property that linear search has, is that I notice that I examine each one of the positions. I don't omit any. So this makes it easier for me to justify to somebody that linear search correctly operates. Because as you're going to see in our proof of correctness, this is going to play a key role in knowing that this algorithm works. So the big thing about this is that once I have identified, we know what linear search is, but I think it's important that I communicate it to you clearly. So I thought this would be a good opportunity for me to talk a bit about pseudocode. So pseudocode is what I would best describe as there's not one universal standard for pseudocode, but it is a way to communicate the algorithm to somebody in a programming-like syntax without having to tether it to any one programming language if necessary. So for example, you're familiar with a lot of standard things in programming, whether it be loops, you know how an assignment operator works, you know how if statements work. We can naturally just describe these things without having to get into the nitty-gritty details of one given programming language. And that's a feature of pseudocode, is that I don't have to tell you in the latest version of C++'s compiler, I can tell you it in a way that no matter which programming language you pick up, you can understand the algorithm. So I'm going to give you some tips for writing pseudocode here as we talk about how I might describe linear search to you. So this is only one of a couple other ways you can describe linear search. So I must stress that this isn't the only description that you can give me for linear search. This is just one that makes it easier for me to prove the correctness of the algorithm. And I must stress that sometimes, especially when you're studying algorithms, the way you present an algorithm may actually help you prove the correctness of the algorithm. Then you could reformulate the algorithm in a way that is better optimized for a computer. So I'll give you an example of what I mean. At some point, I'm pretty sure that you'll see what I mean by this based on how I describe this to you. So here, I'm gonna usually what you'll find is I'll tell you I'm gonna describe an algorithm to you. Just like a function, I'll give a name to the algorithm. In this case, I'll call it linear search. Then I'll write out its inputs. So in this case, I have an array L. Now, optionally speaking, I can include also N because it's an array of length N. In some programming languages, you don't have really an easy access to the length of the array. Sometimes it's better to explicitly write it. However, just for here, I think it's a little easier because I don't write N anywhere else in here. It just makes it a little easier for us to see that that is indeed something related to L, which I can always describe in the input if it's ever unclear to a reader. So I must stress that N technically isn't necessary up here, but I'll describe it over here just for the sake of clarity. I'm going to include both. But you can think of it as just like a function's signature where I have the name and I have my inputs. But notice I'm not specifying the types. That's something if you want to add in, you're welcome to do it. But most certainly it's not necessary because I'm going to describe the inputs to you. So the input of the algorithm is going to be an array L of size N. And I'm going to give you a value X. So do you see how I describe all of the inputs here? So now I'm going to tell you what the output is. So this input-output part should remind you a lot of documenting code. Like often when you write like a function, you usually want to tell what the input is of the function is and what is the return value. This is just very much like the same idea. So here, the output will just be a position I, such that L sub I is equal to X if X is in L. And -1 if X is not in L. So you can see quickly from this inspection that you can say, I'll describe you the input. So this just, remember, this is our definition of an instance in this problem, right? Does everybody see that? Is that the input describes what the instance of the problem is. And for the sake of our convenience here, the output here will just tell me a position. And like I said, if you could easily modify this to be true or false. I do actually will have an example in the notes of showing how you might rewrite this to be so that it tells you true or false instead. It will be included in one part of the examples for proofs of correctness. So I want to make sure you see several examples of these things. So you might ask, okay, so Dan, how are you going to write out the algorithm to us? And like I said, algorithms can be described in words. They can be described in pseudocode. They can be described as actual computer programs. But the idea is I would like to describe the algorithm to you, not necessarily its implementation. So an implementation would be the C++ program. So I want to communicate the idea to you. I don't necessarily want to be like, yeah, no, it has to be this specific C++ program. I want to communicate what the algorithm is, which is I would consider a much more fundamental thing than just one given implementation in one language. So here's an idea. What I'm going to do is I'm going to start off by having a position that I'm going to keep track of. I'm going to call it I. And I'm going to assign it the value of 0. Now, I'll very often use this left arrow to mean assignment. Another way you can write assignment, I know some people like this, I know I used to like it a lot more, was colon and equals is another way of saying assignment as well. So in a programming language like C++, this is the same thing as me writing that, just an equal sign. But remember, it's not an equal sign, it's assignment. So I'm assigning the value 0 to I. So this would be what I might write down in pseudocode. Here's what it might look like in C++. So now this is the thing. This is the thing that gets interesting. Like I said, there's not one universal standard for pseudocode. If you wanted to use an equal sign for assignment, you have to make sure, as mentioned in the chat, you would have to go equals to, just like in a programming language. So the reason why is because we don't want to be ambiguous, right? So in the context of C++, if you write equal to like this, notice that I've not used equals at all here. So I could literally write equals like this. But here's the big but. As long as you're consistent, it's okay. Why? Because if I use an equal sign that means equals to, like this, notice that I'm not using that anywhere else here. These are different set of symbols. This means assignment, that means assignment, but now I've reserved this now for equals, or equal to. However, if I were to use this in two different contexts at the exact same time, that gets confusing. Does anybody see why? So for example, actually, let's do an example here. Let me see if I can find an, let me give you a quick, what I mean by this. So for example, if I were to use something like, say if I was writing a program in C++, and it had a variable called x, and I assigned the value 5 to it. Now, when I write this in C++, I know this means assigns, right? It's an assignment operator. However, if I write then all of a suddenly, if x with one single equal sign here, notice that this actually isn't saying equal to, right? Now that says assign it. I'm asking you to assign x to be 5. And that might mean something very different in a programming language than what you might intend. So do you see what I mean? How it has to not be ambiguous. So if I were to do this in C++, it'd probably, well, first, I would have to check, because sometimes C++ does some fun stuff. But most certainly, it would try to assign x to be 5, right? But that is most certainly not what we intend when I write this. This is why I'm using different symbols for assignment, and if I choose to use this symbol for equal to, I want to use that one, and now I don't have to worry about it being ambiguous with assignment, say in C++. But you can totally, if you want to write your pseudocode where you use assignment with an equal sign like this, and then but you go equals to with 2 equal signs, that's cool too. The key thing is clarity and not being ambiguous. Is that clear? I love that question. That was a lovely question. So if you want to use a different symbol for assignment, that's cool. If you want to use an equal sign for assignment, that's cool. But you have to make sure you use equal to, just like you would, say, for example, in C++. Because that means something else than assignment. I'm just giving you some suggestions to make it so it's a little bit easier and more concise to describe things. So here we go. So I'm going to start off by assigning I to be the value 0. And I'm going to have a while loop. And just like in your typical programming language, you have all your control structures. So I can write a while loop. So I can go while. And I can have conditions. I can check while I is less than n. And I can check if L sub I is not equal to x. I'll do the following. So just like your usual stuff, I could put curly braces here, or I can indent in and put it on the next line, whatever the single line is. That's fine. A lot of the rules that you know about from computer programming are just as applicable here. Just I'm writing it in a very different style. I'm not adhering to all of the syntactical rules of a C++, but if you can easily pick up and describe this in a way that it doesn't matter if this was C++ or Java, you know what the algorithm is. You can understand it. So for example here, I'm going to make it so that I'm indenting in, because this will be just the one line that's going to be inside my while loop. I'm going to assign I to be I plus 1, because naturally I'm going to use this position I as my variable for determining the position that key X might be in. But it's going to get modified in this loop, because notice the conditions of the loop require that I gets modified. Now, I'm going to conclude my while loop, and I'm going to just put an if statement after this. So just like an if statement in your typical programming language, I can have if, and I'm going to check if I is equal to n. Then I'm going to just simply return -1. Otherwise, I'm going to return the position I. I'm going to explain why in a moment, why I wrote it out like this and why this specific setup. So notice that when I refer to the output, I'm usually referring to a return value. So notice that I'm using the key phrase return as opposed to saying print. I'm asking you to return it. So whenever I talk about the output, I'm talking about, in this context specifically, I want to know a position I. Now, you can obviously make it so it prints, but you're going to find in this course, almost always when I talk about the output, I'm talking about returning that value, just like you would with any other function. So I'm just using the same keywords you might be familiar with, like return, and in this case, I'm returning a number. But so first, before we proceed, are there any questions? Now, if you looked at this, now, keep in mind, this is the first time I'm showing you pseudocode, right? Like, this is the first time I'm doing this. If you read this, does anything out here make no sense at all, or does this seem okay? Like, is there anything that's confusing about what I've described to you? Now, I'm not talking about the algorithm itself. I'm talking about the description of this. Like, you could read this and be like, okay, maybe it isn't like C++ like I'm cozy with, but it most certainly describes what you might think of as linear search. Now, obviously, there's some modifications you can make to this, and you can call that linear search too. Okay. So question, why are we incrementing at the top of the loop? Okay. So notice that I have, first I begin by assigning I to be the value 0, and then I have a while loop here. The conditions of the while loop are these two right here. I check if I is less than n, so that's one condition of my conditional statement. The other one is checking if L sub I is not equal to x. But if these are both satisfied, I increment the value of I by 1. So likewise, if I wanted to write this as I++, that's okay. I could totally do that. That's what this means. But notice here that, so let's see. So hopefully that clarifies what's happening. So there is no incrementing happening at the top of the loop. I set up this initial variable before I enter the while loop. So the while loop is this part here, these two lines. So what's happening is this while loop will keep iterating until one of these two conditions fails. Sure, that's going to be a key part of the correctness of this, is these two conditions here. You have to put parentheses. You can put parentheses if you like. That's okay. Notice that here, it doesn't matter that I could quite literally do this. Like, I could do that. That's okay. I can add that in. That's okay. It's about clarity here. But if it really matters that something, they say there's two conditions that have to be this and that, but there's also a potential or condition that is independent of that and condition, then that's when you really need to care about having parentheses around the part involving the and. Could you explain that while part? Sure. So I'm going to explain this in words, verbally, what this algorithm is doing. So first, the algorithm begins by assigning I to be the value 0. Then, while I is less than n and L sub I is not equal to x, we perform the following. I perform I is assigned to I plus 1. Once one of these two conditions is invalidated, meaning that this condition or this condition becomes false. Potentially both of them can become false. Then I exit out of the while loop and I proceed to this if statement. And I check if I is equal to n, then I return -1. Otherwise, I would return I. But yeah, so this is just a description of something that you could easily, if you've seen this, you can probably say, hey, Kate, I can totally take this and write that in C++, right? You've seen linear search before, right? But the thing is, this is not very hard to translate over as long as you understand the algorithm, right? But that's the big piece here is the pseudocode. There is no ambiguity here what this algorithm is doing. There's only one thing I do want to point out for you, and I know that some people might get a little bit stickler about this, is that I'm using this and so if you're wondering what kind of thing this and is, it's the 2 ampersands. So for those that are really interested in these really kind of nitty-gritty details, I'm using the 2 ampersands for the and. The reason why is because in a feature that is known in a lot of programming languages, if you use this double and, it enforces a feature called short-circuiting. So what does it mean? It just means that it'll check the condition, it'll check this condition, then it will check this condition. So the minute if one of these becomes false, it will just straight up evaluate this entire thing to be false. That's what short-circuiting means. So that's why I'm using this. It's not actually just a single ampersand. It's not that. It's 2 ampersands. That permits me to write it like this. Otherwise, I would have to actually take this, put it inside the while loop, and write it as an if statement. So can you explain the second last statement again? This if statement right here? So keep in mind, I'm going to go through some of the important bits here, but this is just saying if I is equal to n, then I return -1. So this is the condition of the if statement. So if you want to rewrite this more like in a way that, keep in mind, I'm writing this in a very compact form. You can easily rewrite this if statement being like this. If I is equal to n, then you can say, okay, I'm going to return -1, close brace, else return I. Like this is me just writing out that same thing I have right over there on the right. No worries, no worries. But yeah, so as we explore more algorithms in the course, you're going to see a lot of pseudocode. So you're going to get very exposed to this. So I want to emphasize a few things. So first thing, notice that this while loop depends on 2 conditions. I is less than n, and else sub I is not equal to x. So notice that this while loop exits when one of these 2 is false because it's an and right here that connects the 2. If it was an or, would that be true as well? If I made this I is less than n or else sub I is not equal to x, would that be still the case? No, right? Because the other one might be true, right? Both of them would have to be false in that case. Exactly, exactly. So remember the ampersand, it's being used implicitly, well explicitly, actually I say explicitly it's being used to ensure this has to be true, this has to be true. If any one of these 2 is false, I exit out of the while loop because I have to do this condition check before I execute the block of code inside for that while loop. So this plays a very big role in how I've wrote out linear search to you. So notice that after I exit out of the while loop, I check if I is equal to n. Now I want you to remember that picture I drew over there of the array where I swept from left to right. So remember I have my array. I sweep from the left all the way to the right. Now every time, notice that there's 2 conditions. It checks if I is less than n, but remember, the indexing of the array starts at 0 and it goes up to n minus 1 is the last position, right? So that means that if it equals n, that means I've gone off the rightmost side of the array. And we don't have anything there that's a part of our array anymore, right? So we want to ensure that we don't go off, we don't start trying to compare the position, like whatever's in L sub n, because that is not a part of the array anymore. That means I've checked everything. That's at least the idea. You can imagine I'm going over one after the other from left to right through each one of the positions. Then there's a second condition. Notice that this condition continues to be satisfied as long as it doesn't equal x, right? As long as L sub I doesn't equal x. But notice that when it equals x, it exits out of this loop, right? Because this condition will then be violated. But what does that mean? That means that, well, look at this. I got to that check because I was less than n, right? Because I had to have checked L sub I is not equal to x, right? And I said that was false, right? But that means that I came across a position at some point. Say here's x right here. I go through this one after the other until I hit x. But if that happens, I exit out of the while loop, right? But what does that mean? That means that I has to be less than n, right? So notice that if I go all the way off the end of the array, I will be n when I exit out of this loop because this condition right here will be falsified when I is equal to n, because it no longer will be that I is less than n. So that means that if I is equal to n, then I didn't find it because I swept from left to right through the array. Otherwise, I return the position that I got. And the reason why, or this is the intuition we're going to see in the proof of correctness, is this position has to be correct because notice that the while loop exits as soon as I find L sub I is equal to x if I is less than n, right? So we're going to see that play out in our proof of correctness. So you're going to see a lot of examples of pseudocode in this course. I'll give you at least a few other examples before, say, when you're working on the first assignment. You'll see plenty of examples. But I want to talk about the proof of correctness here because I've actually laid out a couple of big things. The first thing, and this is I like to lay it out like a game plan. So notice here that if I showed you that this algorithm terminates in finite time, where are the 2 points where it exits? Is it like inside of this while loop? Does it return anything inside that while loop? No, right? It returns either here or there. This is why I presented the algorithm the way I did to you. I could have easily written linear search where I put the return statement inside the while loop. Does everybody see that? Is that I could have easily had it where I do a check and I check L sub I is equal to x, and I could have put the return statement in here. I chose to make it so that this loop exits and it has only 2 possibilities that can happen. This is just to make it a little easier for me to talk to you about the algorithm. But like I said, the argument I'm going to give you, it will still work regardless if you were to take and put this part when you check L sub I is equal to x inside of the while loop. You could have easily put it there too. I just think it's important that you can clearly see the game plan for the proof of correctness. If I show you this terminates in finite time, that guarantees there's going to, whenever I give you an instance, it's either going to execute whatever's inside, whatever the code is for the if statement being satisfied, or it's going to return I. There's only 2 possibilities that can happen. So as we design or develop more careful or more elaborate algorithms beyond this, it's going to become harder to do this. So we're going to see a lot of different techniques for approaching the correctness of algorithms. Some of them I'm going to present to you in a more intuitive way. Others I'm going to give you the bits and pieces that why it works. But the key thing is I want to present it in a way that will convince you that the algorithm is correct. So anyways, I want to talk about the proof of correctness here. So we're going to spend, depending on how much time we get, I'm going to try to get through the proof of correctness with you. If we get past that, we'll start talking a little bit more about complexity and some features that we would like to have for algorithms. So what I'm going to do now is I'm going to go through a proof of correctness here. Now, I must stress that there's many different ways to prove the correctness of an algorithm. And you know how I talked about the whole mayonnaise mustard thing? I'm not expecting you to be some pro at this. Say on the first assignment, I'm expecting it to be like you're in your first experiences trying to do this. I'm not by any means expecting you to be like, yeah, I'm a total pro at this. I'm just trying to expose you to these ideas so you can give it a try. But think about these things very carefully. It's about formulating a clear argument for the correctness. It's not an explanation in the sense that I'm writing you like a little brief explanation. It's actually an argument that demonstrates that it's correct. So just keep that in mind. There's several other techniques that do exist for proving the correctness. For example, and some of these you'll see in some other courses. I know that in CS210 we talk a lot more about these kinds of things. I usually like to expose it to you up front. Then you'll get to have more time playing around with this in later on courses. But you're going to see a common theme in a lot of these things. We're going to be doing a direct proof because I know that this algorithm has two direct outcomes always for any one instance. So I can bucket them into two possibilities. Either I have an instance, it will indeed produce me -1, and that will match those where the array doesn't have key X in it. Then there's the other bucket that has it's going to have all of the possible arrays of some given length n, where they're given also a key, where, for example, that X is in the array. There's two possibilities that can happen. You're going to see how this plays out in the proof based on what we just described over here. But I must stress that there's other techniques. One that if you may have heard of before, mathematical induction. It is used very often also for proving the correctness of algorithms. And the way intuitively they work is it's almost like you're simulating the algorithm, but we maintain something called an invariant. And we're going to see this idea later on in the course when we start talking about data structures, where what happens is every time I do one step in the algorithm or I perform an operation, I would like to know before, during, and after, but specifically before and after, that some property is always satisfied. And I'm going to include an example of this just as optional reading if you're very fascinated about this idea. I'm not going to test you on it. I just want to expose you to it. So it'll be an optional reading if you're curious about mathematical induction and how you can use it to also prove the correctness of linear search. But here, I'm just going to care that we just play around with a direct proof technique. So we're going to first prove that it terminates. So our first claim is that linear search terminates in finite time. So I want you to carefully look at the pseudocode you have probably in front of you. So remember, as long as I can show you that there's going to be some maximal number of steps that happen, at most. It doesn't matter if it happens earlier or later, as long as it happens eventually. That's okay for us. That will guarantee that it's going to terminate in finite time. So you're going to find that my proof is going to very much have the same spice to it. So to prove the claim, observe. So I'm going to make an observation. Often making an observation that's very easy to check is helpful in a proof of correctness. In this case, it's evident because the algorithm literally is going to do what I'm going to say. So you can just point the reader to it and say, hey, look, that's what the algorithm will initially do. Then this will happen. And then you argue that it will terminate because of that. So you use properties of what the algorithm describes, you make some observation about it, then you argue to try to reach your conclusion. But remember, it is an argument. It's an argument. It's not just me trying to explain what the algorithm does. At first, when you first encounter these things, it will very much feel like that at first. That's only because of the technique we're using. Because we're using a direct approach. So we have to observe something, and then there's going to be some possibility of something else happening. So watch this. So observe at the beginning of the algorithm. At the beginning of the algorithm, I'm going to abbreviate algorithm with alg, just for the sake of brevity. Variable I is set to value 0. And now notice that in our while loop, every single time i's value gets incremented by 1, right? But notice that there's two conditions on that while loop. There was I is less than n, and then there was the one checking for equality, right? In this case, inequality. Notice that that while loop most certainly could not execute more than n times, right? Like for a full complete iteration, right? It just can't happen because I is less than n has to be satisfied, right? So I'm just going to use that. So I'm just going to point my finger at that. Okay, well, the while loop requires that I is less than n, so every time the iteration, it will go up by 1 each time, my I. So surely it can't go an infinite number of times. It has to eventually violate that condition. Because n is indeed a finite number, right? So, and after each iteration of the while loop, the value of I is incremented by 1. Now, I'm going to phrase this in a rhetorical way, but most certainly an easier way for me to just say this is, well, notice that I'll include both explanations. That way you can look in the notes if you want to see one way of writing it. I'll show you another way to keep it simple and brief for us. Notice that the while loop requires that I is less than n. As n is finite, it's an integer, right? The while loop must end as soon as I is equal to n. Therefore, the algorithm terminates in finite time. Algorithm terminates in finite time. So notice I have a conclusion stating what I am doing, and I include this box. This box indicates the end of the proof. So are there any questions about my proof here? Are there any things that you could point at and be like, okay, Dan, I don't quite understand that one part of your proof. Is there any holes in my argument here? Any holes at all? I'm open to anything. Because it is indeed a proof. I'm trying to show you that it terminates in finite time. So what about the other condition? That's a wonderful question. So I'm going to remind you actually of, so as I said earlier, there's two conditions that have to be satisfied, right? The first one was that I is less than n, right? That's the first one. That's the one that I used in this proof. But there's also that other one, right? There's this and then it checks if else of I is not equal to x. Well, notice that every single time I perform a complete iteration of the while loop, i's value goes up by 1. So the while loop actually has this condition right here. But there's this other one. But this other one only will lead me out of the loop, right? It's this one that will keep me there as long as possible, presuming that, say, x isn't in the array, for example. But notice that if I really want to know how many iterations may happen at most, it's really the first one that governs that. So even if I exit out early, this one might be still satisfied, right? But most certainly you can exit out early. So the other condition for our proof isn't really necessary, because if I want to just show it terminates in finite time, I'm not saying how fast it actually has to do it. I just know that it has to terminate in finite time, right? So it may exit out earlier, but it most certainly has to be the case that it always satisfies this if most certainly doesn't exit out earlier. Now, of course, we can always add that in more explicitly if you would like. That's one thing you can always add in if you'd like. But notice that this while loop just requires that this is the case. But n is finite, right? So that means that every single time you bump up the value of I, you're going to get one step closer to n. So even if x isn't even in the array, you're going to eventually have to it's either going to exit out earlier or it's going to violate the first condition. But we care about the algorithm terminating in finite time. So this is really the one that is the suspect one. But yes, you most certainly, if you wanted to say add that in and incorporate, I encourage you to do it. I think it's actually a good idea if you'd like. But yeah, no, it's a wonderful question. Yeah, notice that here, the big thing for us is making sure that this thing, our algorithm actually terminates in finite time. So notice I'm not caring about how fast it does it. I just know that it will have to terminate. It can't go any longer than most certainly when this condition gets violated, right? So you can almost look at this like it's some upper bound on how many operations might happen with this algorithm, which might be interesting for next lecture. But yeah, no, it's a wonderful, wonderful question. But yeah, the other part is the correct output part of the proof. I'm going to give you a sketch. Actually, I'll write out a part of the proof and I'll give you a sketch or a briefer description of the second half. That way we can get out on time. But I have the whole proof in the notes here. So I'm going to go through the second part. So this is the part that I would consider probably the trickier, but as soon as you really understand the idea that really all the instances fall in the two buckets, everything actually is a much easier thing to observe. So just remember that if I wanted to show that the algorithm always produces correct output, my goal is to look at what the algorithm does. So we have to always look at what the algorithm actually does. So we actually have to look and see what it does. There isn't not just like one simple way of always doing this. It's always specific to the algorithm. So notice that because we know the algorithm terminates in finite time, there's these two possibilities that can happen. Only those two. So I'll show you, for example, the first case. So notice that there's actually just two cases that can happen. You're going to find the same thing if you design, say, for example, on the first assignment, you might try to design your algorithm so it also breaks into two cases like this. So I'll give you the first case and I'll give you a sketch of the second case. The second case is just very wordy. It's very much based on the same argument I gave over there. It just incorporates the second condition. That's why I didn't elaborate it on, as was mentioned in the chat. It gets elaborated on in this part. So just to abbreviate linear search, I'll use LS. Linear search outputs the correct answer. So this is going to be my claim. And I'm just going to give you a sketch of the proof. I'll write out the full first case. The second case, it's easier for you to explain in words verbally, but I'll give you kind of just a quick sketch of it. So notice that if I look at this final line here, notice that it had to have been the case that I is not equal to n, right? So I is not equal to n. That's why that else statement occurs. But we know the algorithm terminates in finite time, right? So what does that mean, logically speaking? Well, if I is not equal to n, it most certainly didn't violate this condition, right? It violated this condition. Does everybody see that? But what does that mean? That means that L sub I is equal to x. So the final line of the algorithm, returns the value I, right? This is the correct value. This is the correct value to return. As the while loop ended. The while loop ended and I is less than n. Which implies L sub I is equal to x. Really crafty, right? Really crafty. So now you might ask, okay, what about the case? So remember, this is one case. This is when we return I, right? So now we got to look at the case when -1 is being returned. I want to know that that happens if and only if the algorithm, in our case, that the array doesn't contain x. So that's what the second case actually is just saying. And the argument for this is just like actually the proof I gave you over there. It just incorporates the second condition that we talked about. So the second case here, just to give you a quick little. So the second case is just me saying x is not in L. And I'm just going to use this double arrow. This means if and only if. I'll explain what that means in a moment. If and only if linear search returns -1. So what does if and only if mean? It means that if this is true, meaning that linear search returns -1, it has to be that it's true that x is not in L. But it also means that if linear search doesn't return -1, that means that x is in L. So it's a very strong statement in mathematics. It's mayonnaise. But the proof for this, I want you to read this. So I want you to read this second part of the proof carefully, but I'm going to explain it quickly here. So, because I know we got to get going here. So the first thing, notice that every single time I do an iteration of this loop, I want to show you that that is indeed the case. So notice that each time I do one of these checks here, I examined each single one of these, and each one of them tells me that L sub I is not equal to x. Just like when I told you I swept from left to right in the array, the same idea is exactly in the proof. So notice that I will keep doing this over and over again until I is equal to n. But notice that that tells you, because I start I at 0 and I end it when I is equal to n, that means I had to go on through position 0, 1, 2, 3, 4, 5, 6, all the way up to n minus 1, right? So that means that I've examined every element in the array, which means that it's not in the array, because otherwise it would have violated this constraint, right? And that's exactly what the proof says, believe it or not. So if you just take a look at that after class, I'd appreciate it. You'll find it very helpful. But remember, the trick with this proof is to break it into two cases. When it returns when I get -1, or it returns I. You'll find on the assignment when you're playing around with yours, you'll have two cases naturally if you design your algorithm carefully, where it returns true in one case, then it returns false in the other case. And you just argue what happens when it's true. You want to argue that it is indeed the case that it satisfies a solution where the answer would be true. Otherwise, it would be that the algorithm returns false whenever the answer should be false. But anyways, with that being said, when we come back, keep in mind I will post a couple more examples of proofs of correctness in the notes. For example, I'll give you a proof of correctness for binary search, and also I'll give you this example with the induction, but like I said, I won't require you to, or even test you on induction in this course. When we come back, we'll start talking about ideal features of an algorithm and start talking about complexity, how we can measure the efficiency of algorithms. So that being said, I'll say thank you very much and have yourself a beautiful day. I'll see you tomorrow.